If you can't follow right now, please just take a piece of paper, or maybe there's an annotation here to follow along. Okay? I don't want to make it too quick, but yeah, we gotta skip some steps. No, not really skipping, but it's just regular stuff. And the time I was talking about skipping stuff, we could have also written it out. Never mind.
Papa Flamby's Advent Calendar.
Here.
Good morning, fellow mathematicians. Welcome back to day number 2 of the Advent Calendar. And don't forget to check out my Teespring shop. You are going to get 10 to 15% off all the merch over there using the code 42069 at checkout. The discount depends on the day we are in. There's a certain pattern behind it. Also, today on the Advent Calendar over on STEM merch, you are going to get 10% off all hot beverage powered Stirling engines. Put it on your cup of coffee and then it's going to start doing its Stirling engineering thing. Yeah, check it out. Link will be in the description, such as all links to reference videos that we are going to need today. Namely, we are going to take the Laplace transform of the differential equation for the damped harmonic oscillator. This right here is my most favorite Laplace transform. And then we are going to take the inverse Laplace transform of the Laplace transform to arrive at the solution of our differential equation. It's going to be quite a lot of fun. And like mentioned before, all the Laplace transform identities can be found here and also down there in the description by taking a look at the Laplace transform playlist. Now, this one right here is a lot of fun because it involves some clever taking apart of fractions. I think it's really enjoyable what we are going to do here today, and I hope you are going to enjoy it too. Now, what's a damped harmonic oscillator? Imagine you have a pendulum, and for real life pendulums you are going to have friction up here, okay, where our string is basically placed, okay, inside the wall, for example, ceiling, and also we have air resistance, and then it's going to swing, and over time our amplitude is getting smaller and smaller, and at some point our pendulum is going to come to a standstill perpendicular to the Earth's surface. Okay, this is the equilibrium position, the fixed point. We are going to need this later. This is why we have this damping term right here, okay, so we have kind of a non-linear damping going on, or is it linear damping? I don't know, I'm not certain about it. I think it's linear damping, and we also have the eigenfrequency of the system. And now we are going to just make use of the fact that we can apply Laplace transforms linearly and pointwise to the right hand side and left hand side. So on the one hand we have the Laplace transform of 0 being nothing but 0. This is the first step in getting everything done. And now Laplace transform applied to x double dot at first is going to result in this identity s squared plus capital F of s, where capital F of s is the thing we want to solve for. Okay, we are going to isolate it later in the game. Then we are going to have negative s of x naught, x of 0. This is just the initial displacement at t being equal to 0, and then minus x dot of 0. Okay, this is just how it works. That's a certain identity we are going to make use of right now. Now we are going to add the Laplace transform of this part to it. Don't forget we have a factor of 2 gamma that we need to drag along. Now we are going to add 2 times gamma times s times capital F of s, and then we are going to subtract 2 times gamma times x naught. And last but not least, we are going to have the Laplace transform of this thing, which is going to result in plus omega naught squared times capital F of s. Okay, like mentioned before, we are going to isolate f of s, capital F of s. In order for us to do this, we are going to factor out the capital F of s on all the terms where it actually exists. That means here, here, and also here. And other than that, we are going to bring those 3 terms to the left hand side. Okay, that's what we are going to do. So at first we are going to have that we have s squared, and then plus 2 times gamma s, and then plus omega naught squared times capital F of s is hence nothing but, okay, what other stuff do we have? If we were to bring all of this to the left hand side, you might notice that we have x naught, okay, here as a common factor. We can factor it out. So we are going to have x naught, and then we are going to have s plus 2 times gamma, and also we are going to add x dot of 0 to both sides. So meaning we are going to have plus x dot of 0. And now, to finally isolate for capital F of s, we are going to divide both sides by what we have here. Okay, this and that is going to cancel out. Also, we are going to divide it on this side. We're going to have s squared plus 2 times gamma s plus omega naught squared. And also we're going to have 1 over, okay, it's just multiplying everything by the reciprocal of this thing, s squared plus 2 times gamma s plus omega naught squared. Okay, this is what we are having currently. And now we need to play around a tiny little bit. Now here's the plan. In normal case, we now isolated capital F of S and we would like to apply the inverse Laplace transform to both sides, then drag some constants to the outside like this x naught, and then hope for the best that we have some kind of inverse Laplace transform identity at hand that we can just identify as being a certain thing, a certain time dependent thing. Now the thing is, with this part, it gets a tiny little bit more complicated if you take a look at the inverse Laplace transform of a damped sine and cosine wave. Okay, this is the identity that we're having here, or both identities. You're going to notice something, namely that we need something down here of the form something squared plus something other squared. Okay, but this something squared needs to be in weird parentheses, meaning we probably have to complete the square down here, but also the thing that is in parentheses, we need it up here in the numerator, at least for the damped cosine wave. And this is what we are going to inspect now. This is kind of the hard part about it. When I first solved this thing right here, it gave me immense problems because I really couldn't figure it out. I didn't know what was going on. Okay, it was kind of hard back in the days. At first, let us complete the square on the denominator here and see what we're going to get. Now we're going to have s squared plus 2 times gamma s plus omega naught squared. To complete the square, we actually don't have to do much because you might notice that this right here is nearly the binomial theorem. If we had the binomial theorem of something, we're going to get something squared plus 2 times the something times another something plus this another something squared. What is the another something squared that is missing? I mean, we need gamma squared here in order for us to complete the square. Meaning what we are going to do is we are going to say, okay, we are going to add a 0 to this whole thing because you can always add a 0 and it doesn't change anything. Meaning the 0 is going to be gamma squared, and we also have to subtract it yet again. Well, and that does the trick actually, because you might notice that this thing right here is just s plus gamma and the whole thing squared plus, and now omega naught squared minus gamma squared. Okay, this is what we are having right now. I mean, this right here looks good. This is nearly what we need for the Laplace transform. If you take a look at the identity yet again, you might notice that we need something of the form s minus, let's say, b in here. I mean, we don't have a minus yet, but this is not a problem because positive is nothing but negative gamma. So we have a factor of negative gamma when taking the inverse Laplace transform later in the game. This is the exponential term, this is the damping term that we're going to have. But also we need something of the form something squared over here. How can we get this thing to be something squared? I mean, it's a difference of 2 squares, but this doesn't help. We're going to make use of a trick that you often use in Laplace transforms. Namely, you're going to say, well, that thing is nothing but the square root of something, but then squared. Because if you square the square root, you're just going to get the thing out that you had before in itself. And we are going to give the square root term a new name. This is just omega. This in itself is just a frequency of a system. For example, the eigenfrequency. Meaning we're going to have something of the form s plus gamma. Okay, and please keep in mind that the plus gamma is going to result in a negative gamma damping term later, squared plus omega squared. And this is good. This looks way more tame as being the denominator, and we can also make use of the inverse Laplace transform identity that we have found out before in previous videos. Let us plug everything in and see what we are going to get. And I'm going to leave a bit of space to plug in the inverse Laplace transform in a second. So we are going to have capital F of S being hence nothing but. Okay, we are going to have x of 0, and then we are going to have now comes the thing in that I was talking about before. Now, for the cosine term, what we need is that thing that we have in parentheses. We need it for the cosine term to be up here. But this causes us some problems right now, because you might notice that we have 2 gamma here. What are we going to do about this 2 gamma? Well, the good thing is 2 gamma is nothing but gamma plus gamma. And the good thing is, even better, a numerator is additive. Meaning what we can say is we have a fraction which looks as follows. X naught times s plus gamma over the denominator, and then we are going to add to it another fraction which is nothing but x naught times gamma over the other something. Okay, let us break it up like this, and this makes matters way easier. This was the hardest part about solving this thing back in the days. Okay, I'm kind of excited. I love this thing. I really like it, it's a cool thing. So we're going to get S plus gamma divided by, okay, and what are we having down here? S plus gamma squared plus omega naught squared, or omega squared. Name was only omega. Also what we are going to have is, okay, we were breaking it up right now, meaning we are going to get x naught plus gamma right here, okay, divided by this thing, and then plus x dot of 0 divided by this thing. I mean, 1 over the denominator is a common factor on both of those, meaning we can factor it out a tiny little bit. If you can't follow right now, please just take a piece of paper, or maybe there's an annotation here to follow along. Okay? I don't want to make it too quick, but yeah, we gotta skip some steps. No, not really skipping, but it's just regular stuff. And the time I was talking about skipping stuff, we could have also written it out. Never mind. So we are going to have x of 0 times gamma plus x dot of 0, all of this in parentheses, times 1 over, and then we are going to get our regular term s plus gamma squared and then plus omega squared. And this is good because now we have something that looks like those Laplace transform identities for the damped sine and cosine waves. One thing is missing though, namely, if we want to get a damped sine wave, we need to have the part that we are squaring here also up here in the numerator. How can we get it up there in the numerator? It's actually pretty easy. Just some simple manipulations, simple algebraic manipulations that you can do. Namely, you can always expand fractions by omega over omega. If we were to expand the fraction by omega over omega, we are going to get exactly up here in the numerator what we need to get our sine wave, our damped sine wave, but also we are going to get 1 over omega on the outside, okay? And since the inverse Laplace transform is also linear, we can bring constants to the outside. And now this works out. Let us now apply the inverse Laplace transform to both sides and see what we are going to get. Okay, I'm using it here because, like I said a second ago, our constants can be brought to the outside. Okay, and also an inverse Laplace transform of this part. Now, we can just identify now. The inverse Laplace transform of capital F of S is by definition nothing but x with respect to t, the solution to our differential equation. Also, we are going to get the initial displacement at t being equal to 0. Then this is going to be multiplied by, well, just our damped cosine wave. Namely, this is going to be e to the negative gamma t, like mentioned before, times the cosine of omega times t. And what we are going to add to it is, well, just this constant multiplied with the damped sine wave, where we have omega t in the argument of our sine. Okay, meaning we are going to add to it this terrible term. Namely, I'm going to put it down here, x of 0 times gamma plus, and this is going to give us x dot of 0 divided by omega, and then times e to the negative gamma t times the sine of omega t. And voila, ladies and gentlemen, this right here is the most generalized version of the damped version, okay? There is no critical damping involved or something of the like, okay? This right here is just the damped version, but the most general one. You can plug in all the initial values that you got without having a phase shift in there at first, and you are going to get all your solutions out, which is really beautiful if you ask me. And don't forget, the omega that we are having here is being just this part, okay? Square root of omega naught squared minus gamma squared. Also, unit-wise, everything fits, okay? If you just compare units right here, gamma has units of 1 over seconds, meaning we are going to get just everything nice unit-wise. So just to, take a piece of paper and try it out if the units fit, but this is a good way to test if you got your Laplace transforms right and your inverse Laplace transforms. But we would like to go a step further, because this right here is certainly not what you are going to find in textbooks. In textbooks, you are going to find a formula for x of t being nothing but some amplitude a times a damping term times some sine wave with a phase shift in there, or cosine wave. Really doesn't matter, you can shift it around however you wish. And we want to get to this point. I mean, I love this one way more because you have all the initial conditions already in there, but we are going to get to the point where you can just take a look at your formulas being the same one as in the textbooks or your lectures on physics. And for this we are going to take a look at the phase space at first, and then we are going to do the same argumentations we did with the previous Laplace transform videos. Now, what does the phase space of a damped harmonic oscillator look like? We are going to draw a phase diagram once again, where we have x dot right here, our angular velocity on the x-axis basically, and our angular displacement is going to be on the y-axis. So meaning our angular velocity is dependent on our angular displacement. Now, what is going to happen with the damped motion basically? So what about our amplitude? I mean, at first it's going to look like we have the same amplitude, but over time it's getting smaller and smaller up until it's 0. We don't have an angular displacement anymore. Meaning at first we are going to have a displacement here, and then there, and then there, and there, and there, up until we reach 0. Now what about the velocity? The velocity is ultimately dependent on the amplitude we are going to have, okay? On the maximum displacement. Meaning our velocity is getting slower and slower the more we get to the equilibrium position, the so-called fixed point, which is exactly at 0. Meaning our x-axis also looks something like this. And this thing is called a spiral in nonlinear dynamics because it looks like this. Our phase space, our phase diagram, is going to propagate more and more towards the center of the so-called spiral, where this right here is our fixed point and everything is going to propagate to an equilibrium position. This right here is a spiral, okay? Just as a little matter of fact for those of you who have never seen this before. And you can actually find a spiral here also on this nonlinear dynamics and chaos poster, which I find to be really nice. Took me ages to make, but yeah, you can find a stable spiral here. It's called a stable spiral because you have a stable fixed point right here in the center, and this applies to our damped harmonic motion. Now we can also draw a little trigonometric thing right here into our phase space diagram yet again, like I did before. Namely, we are going to draw a triangle into here and see how all of this pans out. Let me enhance on the triangle a tiny little bit. Now the triangle is going to look like this, okay? So this right here is an initial displacement, phi naught, and now we are going to give all of those that we have here, those constants in the front, a new name. Let's say x of t is going to be of the form a times e to, what we can do is we can bring e to the negative t to e to the negative gamma t to the outside. Let's do it like this. And then this thing right here, this initial displacement at x being equal to 0, is going to be nothing but cosine a times cosine of omega t, and also this huge term is going to be nothing but b, okay? B times the sine of omega t. And by the same arguments we had before, we are just going to say that, well, the thing that we are having here, this length basically on our x-axis, the angular velocity axis, is going to be b, okay? Watch the other video for the arguments, okay? I explained it there. And this part right here is going to be a. And overall, what we are having here, this hypotenuse, is nothing but the amplitude in our phase space. We are going to call this thing capital A, and capital A is nothing but square root of a squared plus b squared. This is just how triangles work. Now you might notice something. We have that our b divided by capital A is nothing but what? This is nothing but the cosine of our phi naught. This is cosine of phi naught. Now, A divided by capital A is going to be nothing but the sine of phi naught. But how are we going to get to those identities right here in this equation? Well, we can just expand this whole thing by capital A over capital A, meaning we are going to have a capital A out here, and we are just going to divide those two terms by capital A. And now you might notice something. What we are having here in parentheses is hence nothing but, okay, A divided by A is going to be the sine of phi naught times the cosine of omega t, and then plus, and B divided by A is the cosine of phi naught times the sine of omega t. And well, this thing right here, I have used it before, is just a trigonometric identity for the addition formula of our sine. This right here is going to give us the sine of just those two arguments added together. Omega t plus phi naught. And this right here, et voila, ladies and gentlemen, is the thing you are going to find in most textbooks, namely x of t ultimately can be rewritten in terms of an initial phase shift as being nothing but some amplitude a times e to the negative gamma t times the sine of omega t plus phi naught. Okay, and this basically settles it. There was a lot of explanations, but I love this thing. I hope you did understand everything, and I hope all the annotations were on spot. I didn't want to write everything out yet again, okay, all the Laplace transform identities, because it's kind of redundant. We have done it before. You can just take a look at the reference videos, and also there were some annotations here, so that basically settles it. If you have any other questions, please let me know. Other than that, don't forget to check out the deal over on Teespring and on STEMmerge, and I just love how this looks. All the initial values in here, all the initial conditions, it's just a bliss to look at. I just love when stuff like this gets so nicely simplified using Laplace transforms. They are such a mighty tool. I just love it. Yeah, other than that, and I love looking at this thing. It looks so fucking good. Trust me, it's amazing. I'm getting goosebumps on my right leg. No, I don't, but that would be funny. Other than that, thank you guys for watching. If you enjoyed this video, please like and subscribe and comment channel if you want to support channel a bit more. Buy those teachers I create a support channel on Patreon. Until next video, I wish you guys a Hagoromo Chak day. Ciao!